Hi there, I'm Clément Roblo. In this series, we're having a look about how to generate random numbers in embedded system, in that case in the NRS52 development kit. In the first video, we saw how to measure our randomness and how to qualify how good or bad it is. In this video, we're going to see how to generate better random than what we had before. Before that, what we just did was an analog measurement from the ADC on board that is not connected to anything and just measuring the noise on it. It turns out that to generate random, you're going to have to use most certainly an external phenomenon. Typically, if you go on random.org, they use atmospheric noise to generate the random that they got. Us, we cannot really measure atmospheric noise, in most systems at least. So we're going to have to be creative about what we got at our disposition. As said before, we got the ADC measurement that can be used. You can measure, for example, the VCC of your microcontroller or the level of your battery, for example. Other sources of randomness could be human interactions. When a human presses a button, that press arrives at some random amount of time when you measure it at very small scale. In the same manner, when the human presses a button, the time that the human presses the button and then release it, that time is going to be random when you measure it at a very fine scale. A human does not know if he presses a button for 1 millisecond or 10 milliseconds. So there you can find some randomness. If you got a microcontroller that is communicating with other devices or accessing to some type of a network, the time delay that each and every communication takes to be processed and answered back, that time got some randomness in it in some cases. You could get some of it there. In more advanced systems, I know that you can get some randomness from the jitter of clocks, for example. Another phenomenon could be temperature or basically any analog measurement that you get. The movement of your device, if you've got an accelerometer or gyroscope of some sort on your board. You're going to have to mostly be creative about how to get some good external values that are supposedly random. The more sources you get that are uncorrelated, that's going to be important. Typically, the gyroscope and the accelerometer certainly have some correlation. So that combining those two might not yield the best results. Mixing the accelerometer and some network delay could be a better match. We'll see how to merge different sources of randomness. But for now, as we saw in the previous video, if we use the ADC, we can get something that is not too bad, but is definitely not great. One of the biggest issues that we got in that case is the fact that our values are very small. We're measuring an ADC that is connected to nothing, so the values are obviously going to be small. So there, what we're going to do is actually combine multiple of those values to generate a full byte of randomness. So there we are back into our random generator program. If you want to have more information, go back to the first video where I explained a bit more. Every time we get a sample, we get a call to that function and those samples coming from the ADC. What we were doing before that was just displaying them as is, but knowing that we got just small values, then what we're going to do is we're going to just wait for two values to arrive and we're going to combine them. The first value is going to be the 4 lower digit of our samples that we're going to ultimately send to the computer, and the second sample is going to be the 4 higher bits of our new random numbers. That way, before that we saw that we had up to 5 bits of randomness inside of our byte, so we're just taking the 4 lowest bits. Hopefully the 4 lowest are the most random one among the 8, and taking 2 of them, sticking them together to make a full byte. That's what this small contraption is just doing. How we getting the first sample? Yes, then we save it. And if it's the second sample, then we combine them together, we print them, and we reset up for the next run. If we look at the results of that one, So there, as expected, we just combine two random numbers, two random numbers, and we get a way higher entropy, 7.33. Already quite nice. So that means that we get up to 8% of compression in that. A lot better compared to the around 5 that we were getting before. For the chi-square distribution, we are still not good. We are at 0.01%. As a quick reminder, that number to be considered as good should be between 10 and 90%. So there we are extremely bad. Then we get the arithmetic mean value that is at 131 in that case. A lot better than before, still not perfect, but a lot better. The issue before that was we had only very small values between around 30, 40 x, 14 hexadecimal. As values, which is okay, nice, but not enough to fill out the FF range. So there, by combining two of them, we get a higher spectrum, and of course the average goes up and kind of close to what we would hope for. Could be better. Monte Carlo simulation, also not amazing. Approximating P at 2.78 is not the best approximation, but still we doubled the precision compared to last time. And then for serial correlation, we get a correlation of 0.46, which is already better than before, but still definitely not good at all. Fantastic. Now what we could do to add on top of that, another system, will be to mix with other sources of random. Here, what we're just going to do is we're going to count the number of samples that we're getting. Every time we get a new sample, we do +1 on that counter. So that's going to be a static. We're going to do 8 and sample counter. It starts at 0, and every time we get a new sample, we increase it. The idea is that every time we are going to send a new sample to the computer, we're going to XOR that value, that sample counter, with the combined samples that we built before. So that means that combined sample is our sample counter. There we go. And there we are starting the capture. Where we increase the speed of the timer to only 10 milliseconds between every sample, so we are going a lot faster than in the last video. There, we got around 1000 samples. We can stop that and we can run the analysis that we're getting. And so what we're getting is those numbers, and if I display below the one we had with just the two ADCs, we see that we jumped from 7.3 bits of entropy to 7.8. So that's going to be 8% of compression. We went to 2%, which is a good improvement already. The chi-square is at 6.19. Amazing. Would not have expected such a great result. So still not amazing, but a lot better than the 0.01% that we had before. The arithmetic mean got a little bit worse. It got a little bit worse, but nothing very significant in that case, actually. The Monte Carlo simulation got a lot more precise at 3.58%, and the serial correlation is fairly similar. So all in all, just adding that counter and XORing it with the values that we got actually improves stuff quite drastically. You could do the same thing of XORing more and more random sources of information to actually mix them together and get better results in theory. Try them. In theory, when you XOR a value, you can absorb its randomness, but you're not going to dilute your own randomness. So that's a fairly safe thing to do. Do the test every time to see does it improve stuff or not, just to be sure. If you keep on doing that type of mixing of random sources, you can end up with something that is actually truly random in the sense that it comes from outside. There is no algorithm involved in it or anything. So by mixing a few of those random sources, you can actually get something that you could get better results at what we are getting here if you pay attention to different sources and mix them well together. You could end up with something that is quite good. One of the main issues that we got with that technique is that it's quite slow. It relies on sampling the world and different measurements that are going to use a lot of energy. A lot of devices run on batteries. So we can do that if we need to, but that'd be great if we could avoid doing all that together. And for that, we're going to have to dive deeper into pseudo-random number generation. And we'll see that in the next video. See you! Crabman, Crabman, Crabman. Mr. Crabman. Thank you, Mr. Crabman.